In this lecture, we will be discussing the Euler's phi function or the Euler's Totient function. Okay, so Euler's phi function denotes basically the number of positive integers less than a number n and which is relatively prime to n. Okay, for example, if you want to find phi of 6, you have to find out the number of positive integers which is less than 6 and relatively prime to 6. So what are they? So the number of positive integers which is less than 6 is 1, 2, 3, 4, 5. Even if you consider 6 also, which of these numbers are relatively prime to 6? 1 is relatively prime to 6, 2 is not relatively prime, 3 is not relatively prime, 4 is not relatively prime because 4 and 6 have a common factor 2, 5 is relatively prime, and 6 itself is not relatively prime because 6 have common factors. So there are only two numbers which is less than 6 and relatively prime to n. Okay, so even if you take which is less than or equal to also, still the number would be same. So different books have different definitions, but the basic idea is the number of positive integers which is less than 6 and relatively prime to n. Okay, both the definitions are also correct. Okay, so that is called Euler's phi function. So here we have given a table of values for Euler's phi function. The value for phi of 0 is trivially taken to be 0. It's based on notational convenience, and also the phi of 1 is fixed to be 1. Okay, just for notation purpose. But you can say the value of phi of 2 is 1. There is only one number which is less than 2 and relatively prime to 1, that is 1. Phi of 3 is 2, phi of 4 is 2, phi of 5 is 4, phi of 6 is also we have discussed is 2, phi of 7 is 6, phi of 8. What would be phi of 8? What are the numbers which are relatively prime to 8? 1 is there, 2 will not be there, 3 is there, 4 will not be there, 5 is there, 6 will not be there, 7. So only 4 numbers are there. Okay, and you can see that when you have prime numbers, phi of p will be, because prime numbers have no other common factors except 1 and p itself. So the phi of p will be p minus 1. That is why you are getting phi of 11 is equal to 10, phi of 13 is equal to 12, phi of 7 is equal to 6. Okay, so for prime numbers, phi of p will be equal to p minus 1. And also generally, phi of m into n is not equal to phi of m into phi of n. Okay, for example, if you consider phi of 4 into 2. Okay, so phi of 4 and phi of 4 into 2 is phi of 8. What is phi of 8? Phi of 8 is 4. What is phi of 4? Phi of 4 is 2. What is phi of 2? Phi of 2 is equal to 1. So you can see that generally phi of 4 into 2 is not equal to phi of 4 into phi of 2. Okay, why? Because phi of 8 is 4, but phi of 4 is just 2. Phi of 2 is equal to 1. So you are not getting result. But if m and n are relatively prime, you have a good result, which is phi of mn is equal to phi of m into phi of n. Okay, for example, if you consider 2 and 5, okay, 2 and 5, they are relatively prime. So phi of 2 into 5 is phi of 10. What is phi of 10? Phi of 10 is 4, phi of 2 is 1, phi of 5 is 4. So 2 into 4, 1 into 4, you are getting 4. So if m and n are relatively prime, definitely phi of mn is equal to phi of m into phi of n. You can get a proof of this result in your textbook also. It's a simple result, but this is the general property. So what we will be doing today is that we are going to prove the famous Euler's little theorem, which states that if a and n are relatively prime integers, then a raised to phi n is congruent to 1 modulo n. Okay, it's a very important result from the point of view of congruences, because you can simplify many congruence relations using this Euler's theorem. Okay, so just look at the theorem once again. Suppose a and n are relatively prime. Suppose GCD of a n is equal to 1. You can write it down. A raised to phi n is congruent to 1 modulo n. Okay, we'll prove this result today. So this is called Euler's theorem. And you may have seen the Fermat's theorem, which states that Fermat's theorem is a special case of this Euler's theorem, which states that a raised to p minus 1 is congruent to 1 modulo n, 1 modulo p. Okay, so that is because if p is prime, your phi of p would be p minus 1. So definitely this is a special case of the Euler's theorem, okay, where p does not divide a. Okay, so a raised to p minus 1 is congruent to 1 modulo p, because in the case of prime numbers, the phi of n will be n minus 1. So there's a Fermat's theorem which we will study later on after we introduce primes. So that Fermat's theorem is a special case of Euler's theorem. Okay, now let us try to prove this result. Okay, so you consider n. Okay, and for phi of n, you are going to consider the numbers which are less than n and relatively prime to n. So let your numbers be a1, which is strictly greater than 0, and a2, etc., a5. So you have phi n numbers which is less than your n. Okay, so you have these many numbers, so phi n of numbers which is less than n and relatively prime to n. Okay, so let this be the numbers. Okay, what I'm going to do is that now your a and n are relatively prime. I'm going to multiply each of these numbers by a. So you'll have a into a1, a into a2, a into a phi n. Okay, so remember here a1 is an index, so this may be some, for example, I'm simply saying it may be some 2, 3, etc. Suppose your a is 5, so your new set will be 5 into 2, 10, then 15. You will be getting a new set like this. That's it. Okay, so initially you had n, you found out phi of n, and you are actually stating those numbers which are relatively prime to n, which is a1, a2, etc., a phi n, because there are a phi n numbers. Okay, now what we are going to do is that, so you know that this is strict, these numbers lie between 0 and n. I am going to multiply these numbers by a, so you will be getting a new set a1, a2, etc., a phi n. Okay, so these numbers can be greater than n. So what I am going to do is that now I will find the reminders when these numbers are divided by n. Okay, I will find the reminders when, for example, in this case you had 10, 15. Now I will divide this by n and get the remainder. Okay, so the notation for that is I am going to take a1. So this means that the remainder when divided by n. So this notation means the remainder when divided by n. So I'll just be using this notation for simplicity. So I'll be considering a1, a2, okay, a phi n. Okay, so I'm going to divide these numbers so that my matters are simplified, and I'm going to find the reminders when divided by n. Okay, now what I'm going to claim is that this set of numbers is just the same as your a1, a2, etc., a phi n. So what I'm going to claim is that these set of numbers is just this set itself. Maybe they have been rearranged in some other order. Okay, so that's why I'm calling this set notation. So these numbers, I'm going to say that there are actually phi n of these numbers, and they may be reordered. That's it. Okay, so actually this set, both the sets would be the same. That is what I'm going to claim here. Okay, let us see. Okay, so first of all, I am going to show that there are actually phi n of these numbers here. That is, actually there are phi n distinct numbers. So in some cases, if you divide, the remainders may be same, so the set total number could be reduced some cases. But I am going to say that it is not the case. That is, actually you are going to get phi n different numbers. How is that so? For example, suppose maybe your two numbers aai and aaj had the same remainder when divided by n. Suppose they left the same reminders when divided by n. Okay, what does that mean? That means that aai is congruent to aaj modulo n. That is why they are getting the same remainder, right? So they are leaving the same remainder. You will get, suppose two numbers are same, that means both these numbers left the same remainder when divided by n. That means your aai is congruent to aaj modulo n. What does that mean? Means n divides a into ai minus a into aj, right? By definition of modulus. So that means n divides a into ai minus aj. But you know that a and n have GCD 1, that means they have no common factors. So if this is true, this means that n should divide ai minus aj, because you know the result that if n divides ab and if n does not divide a, or if GCD of n comma a is equal to 1, then n divides b. You know the result from previous classes. So from that notation you will have n divides ai minus aj. But what do you know about ai and aj? Oh, you know that ai and aj are actually lying between 0 and n. Okay, so if this has to happen, if ai minus aj, if n has to divide ai minus aj, this number is anyway strictly less than n. Okay, ai and aj are less than n, and if ai minus aj, if n divides ai minus aj, that means there is only one possibility, that is your ai minus aj should be equal to 0. So only this possibility would be there, because this your bound is between 0 and n. Okay, so this means that ai minus aj is a multiple of n. So n into some other multiple. So is that possible? Because n is anyway greater than a and aj, so this cannot be a multiple of n. That means only one possible multiple is 0. So that means your ai should be equal to aj, that is If two of these numbers are equal, that means essentially the index would be the same. Okay, that means that all these numbers AA1, AA2, all these numbers AA1, AA2, etc., A phi n, all these numbers are essentially different and you have phi n of them, right? And moreover, so you have phi n numbers. So already you had earlier from phi n numbers were there with you. What were they? It was A1, A2, etc., A phi n. So you had earlier phi n numbers which were less than n and relatively prime to n, which were relatively prime to n and less than n. Now you are getting a new set of numbers which is actually less than n only, because these are reminders. Okay, and also they are phi n in number and they are distinct. Now I am going to show that they are also relatively prime to n. I will also show that they are relatively prime to n. So what is the benefit of that? Then that means that essentially both these sets would be the same, because these are also positive integers because they are reminders and they are less than n. Phi n of them are there, and if it is relatively prime to n, they will be actually equal to this set, which is essentially the set of integers which is less than n, positive integers which is less than n and relatively prime to n. So I will show that these numbers are relatively prime to n also. Okay, so you take some ai, so remainder of ai, so this is my set here. So I will show that this ai and n are relatively prime to each other. Okay, we will show that these are relatively prime to each other. Okay, now tell me, can n divide ai? Can n divide n? So you know that n and a are relatively prime to each other. N and ai is also relatively prime to each other, because by definition, by the theorem, n and a are relatively prime to each other, so there are no common factors. And n and ai, you have chosen ai in such a manner that ai and n had no common factors, right? So that means n and ai are relatively prime to each other. Is that clear? Okay, so when you found out GCD, I hope you remember the Euclidean algorithm. In Euclidean algorithm, it was GCD of Mn is same as GCD of m minus qn comma n. That means remainder comma n. So similarly, so if GCD of Mn is equal to 1, this should also be equal to 1, right? So if GCD of ai comma n is equal to 1, what would be the remainder when ai divided by n? What would be the GCD of that? That also should be equal to 1, right? Because by Euclidean algorithm, if GCD of Mn and n is equal to 1, the GCD of remainder and n should also be equal to 1. So using the same logic here, if GCD of ai and n is equal to 1, because they are relatively prime to each other, then the GCD of the remainder when ai is divided by n and n itself would be 1. So that means ai comma n, GCD of this should also be equal to 1 from that result. So you see that AAIs are relatively prime to n. Okay, so that means these sets, this set contains actually exactly the phi n positive integers which are less than n and relatively prime to n. Okay, so these two sets are essentially the same. Only difference may be that this may be in some other order. For example, if this is like some 1, 2, 3, this may be written as some 3, 1, 2. So it may be a permutation of the elements. Okay, so now you have got that. What have you got now? Your A1, A2, A phi n. Okay, so suppose I am going to multiply this set, every element. This will actually be equal to AA1, AA2, right, A phi n. Okay, this will be both will be the same. Why? Because essentially both the sets are the same thing, and you are getting the only thing is they have been permuted at best. And actually, so if you multiply everything, you are getting exactly phi n terms here, and the same phi n terms would be appearing here itself. The same phi n terms would be appearing itself here itself. Okay, I hope this is clear. Okay, so now you know that if you have a number a, for example, some other number x, if you have some other number x is always congruent to x mod n, right? Why? So that is, if you divide x, you subtract the remainder, divide x by n. If you divide the x by n, and you are subtracting the remainder, okay, from x, that will always be a multiple of n. Okay, so using that result, you know that x is always congruent to x mod n. Okay, so using that same logic, you have ai is congruent to ai, this quantity, which is the remainder when divided by n modulo n. Okay, so ai would actually be equal to the remainder ai using the same logic here, ai mod n. Okay, so I can say that aa1 is congruent to aa1 modulo n. Okay, similarly aa2 is congruent to aa2 modulo n. Similarly aa phi n is congruent to aa phi n modulo n. So multiplying all these congruences together, so we know that if a is b is congruent to b mod c, similarly some x is congruent to y modulo z itself, you can actually multiply them. Okay, so using that result, it will be aa1 into aa2 into etc. aa phi n. Actually it will be congruent to aa1, okay, aa2 etc. aa phi n modulo n. Right? Now what is this? How many a's are there? There are phi n terms are there. So a raised to phi n terms will be there. Then you will have a1, a2 etc. A phi n will be here. And you know that this quantity is actually equal to your a1 into a2 into etc. a phi n. So I will replace it here. So it is actually equal to, it's congruent to a1 into a2 etc. into a phi n modulo n. Okay, what does this mean? This means that n divides a raised to phi n a1 a2 etc. a phi n minus a1 a2 etc. a phi n, or n divides, what are you getting? I am taking the common factor here, a1 a2 etc. a phi n, which is the common factor, into a raised to phi n minus 1. Okay, now you know that these a1 a2 etc. a phi n are relatively prime to n. Okay, so if a divides bc and if a and b are relatively prime, it means that a divides c. Okay, so from this we will get that if n divides a1 and a1 and n are relatively prime, so n will be dividing a2 into this. Again, n and a2 have no common factor, so n will be dividing the rest of them. So that means successively using that result, you will be getting n will be dividing a raised to phi n minus 1. That is because none of these factors, none of these terms have any common factors with it. So n will be dividing a raised to phi n minus n, or in other words, you are getting a raised to phi n is congruent to 1 modulo n, which is your Euler's theorem. So this is the statement of the Euler's theorem. Okay, it's very simple. So how will you do it? It's very simple logic. So this I hope, just go through this once again. So Euler's theorem was here, yeah. So a and n are relatively prime integers, then a raised to phi of n is congruent to 1 modulo n. So what is the first step? First you take all the n integers which are relatively prime to n, right? So you take the integers a1, a2 etc. a phi n which are less than n and relatively prime to n, and you know that they lie between 0 and n. Okay, then you multiply each of them by a. So you are getting a1, a2 etc. a phi n, right? Now we are going to take the remainders when divided by n. Okay, so you are getting some set of remainders. Now what we claim is that this set of numbers and this set of numbers is essentially the same. Okay, for that first we show that all the numbers here are distinct. So I will show that aai is equal to aaj means that ai is equal to aj. It is very easy to show by the definition of congruence itself. So we will be getting 5j distinct numbers. Okay, once they are distinct, we will show that aa is actually relatively prime to n. ai and n are relatively prime. That also can be done by the use of Euclidean, the lemma used in the case of Euclidean algorithm. So you are getting that essentially these things are the same. So their product will actually be equal to same. So their product will actually be the same. Okay, now you are using this result to show that aa1 is congruent to aa1 mod n, aa2 is congruent to aa2 the remainder and modulo n, and you multiply it together. So you will get this quantity, and you will be replacing this by your a1 into a2 into a phi n. Okay, so from this you will take the common factor outside, and you will get n divides a1 a2 into a phi n and a phi n minus 1, which means that n divides a phi n minus 1 because each of them are relatively prime to n. So this means that a raised to phi n is congruent to 1 modulo n, and that is the proof of your Euler's theorem. Okay, thank you.